Hi everyone, my name is Vincent Ribli, and today I'd like to tell you a bit more about my final year project, which is titled Over-Parameterisation for Single and Multitask Learning. To give you some background, our industrial partner is working on autonomous vehicles. And if you imagine an autonomous vehicle, it is a vehicle which is able to move on its own with minimal human interference. To do so, the vehicle needs to be able to make sense of its environment. And how it is able to make sense of its environment is by doing tasks such as semantic segmentation, where it tries to give context to its environment. It needs to do depth estimation, estimating how far away objects are from the vehicle. And you need to also estimate the surface normals, where you estimate the angle of the normals of the objects around it. And to do so, you would make use of computer vision techniques. When you do computer vision techniques on an autonomous vehicle, there are constraints which are unique to an autonomous vehicle. For example, you want the inference to be performed with a high performance. For example, when you want to do semantic segmentation, trying to detect whether there are people around the vehicle, then there needs to be a certain performance requirement that needs to be met so that you can sufficiently detect that there are people around the vehicle. Also, there are latency and hardware accelerator constraints. So given the hardware accelerator in the vehicle, how do you make sure that the prediction is fast enough so that, let's say when there are people around the vehicle, you can have the prediction immediately so that the vehicle can make a decision to not endanger the people around the vehicle. Secondly, as you see here, the vehicle needs to perform semantic segmentation, depth estimation, and surface normals estimation. So multiple tasks need to be solved simultaneously at the same time. And this is a system engineering problem, because how do you do that? Do you have different models to solve the different tasks, but this would put a strain on the hardware accelerator? Or could you design a model to solve all the tasks at the same time using a single model? And if you want to do that, how do you do that? So these are two constraints which are unique to an autonomous vehicle setting, which would be the motivation for our research. In the first constraint, we want the inference to be performed at high performance within the given constraints. And so, let's say that we have a base model. The base model is used to solve a task or some tasks which are needed by the autonomous vehicle. And now when you want to improve the performance of the model, typically we would expand the model into a larger model, for example in the research paper of EfficientNet, by adding the number of parameters to increase the performance. But we cannot keep on adding number of parameters, as this would put a strain on the latency and hardware accelerator. So what we would do is to suggest a technique called over-parameterization. What is over-parameterization? So this is a procedure where you can use the same number of parameters at inference time but have a higher performance. So in the first step, you would want to expand the original base model into an over-parameterized model using more parameters than the base model. And after that, you would train the over-parameterized model, and you could possibly integrate alternative training routines to maximize the performance. And after doing that, you would want to compress the over-parameterized model into the original base model using a mapping defined by the type of over-parameterization which you are using. And based on the existing research, such as in RepVGG and factorized neural layers, they have found that by doing this process, you could have the same number of parameters at inference time, yet the performance is increased. So this is a very interesting phenomenon which will be investigated in our research. In the second constraint, we want to solve multiple tasks at the same time. And just now we suggested the idea of using a single model to solve multiple tasks. So how do you do that? There is a technique called multitask learning, and one of the more common implementation is through the use of shared layers and task-specific layers. So shared layers, let's say in a neural network setting, means that the first few layers of the neural network is shared by all the different tasks. And after which, this would branch off into task-specific layers, where each of the branches will solve the individual tasks. And by doing this process, it has been found that not only is it more efficient because you use one model to solve different tasks, It has also been found to improve the performance because by doing this setup, it improves generalization. So we will investigate multitask learning as well. So in our project, we have two main objectives. First of all, we want to develop a novel technique to perform overparameterization and see how it performs against existing techniques. Second, we want to design alternative training routines in the training step of overparameterization to improve the performance. And we will design different routines for single and multitask learning. We have tried this overparameterization using the Cypher 100 dataset, which is an image classification task. And we have found that by using our new overparameterization technique along with the alternative training routines, we have had a better performance compared to the baseline, which is without overparameterization. And also we beat the performance of factorized neural layers and also Rep-VGG. So this is a promising result. We also tried our new overparameterization technique on the NYU V2 dataset, which is a multitask dataset where you need to do semantic segmentation, depth estimation, and surface normals estimation at the same time. If you can see from the charts, you can see that for depth estimation and surface normals estimation, our new overparameterization technique with our alternative training routine number 1 has beaten the performance of the baseline and also all existing techniques. And also, for semantic segmentation, our new technique has beaten the baseline, although in this case, Rep-VGG is doing better than our new overparameterization technique. But in the other tasks, we see that Rep-VGG is not doing as well. So we can say that our new overparameterization technique is doing consistently well in all the 3 tasks. And so we find that this result is quite promising. In our research, we have uncovered very interesting results with the use of our new overparameterization technique. And I'm very excited to see about the research directions and possibilities that this opens up. So thank you for listening to my presentation, and I hope you have learned something new today. Thank you so much.